A very good morning, ma'am. This is Mohammed Hanif J from second CSCB section, and the topic for my presentation is half adder and full adder. Now let us see the introduction to adders. So, what are adders? Adders are fundamental digital circuits used for arithmetic operations. They perform the addition of binary numbers, which is critical in computer systems. Understanding half adders and full adders is essential for designing complex arithmetic circuits. We will now learn the functionality of two types of adders, that are half adders and full adders, along with truth tables and logic diagrams respectively. See, basically the adders are nothing but for the arithmetic operations on binary numbers, in a sense the assembly level language of computer. These play the crucial role. And in this presentation, we'll learn what are half adders and what are full adders. What is a half adder? A half adder is a combinational circuit that adds two-bit single-bit binary numbers. It produces two outputs, the sum and the carry. The half adder is the simplest form of an adder circuit. So here in the half adder, we give the input as 2 bits and we get the output as also two outputs, that is, one is sum and the other is carry. See here, you could see the diagram of half adder below. Let us study the truth table of half adder. The truth table outlines the relationship between the inputs and outputs of a half adder. It shows all possible combinations of inputs and their corresponding sum and carry outputs. The table confirms that when both inputs are 1, the carry is generated. See, like you could see in the truth table, input, output, A, B, sum, carry. See, 0, 0, it results in 0. And sum was also 0, carry is also 0. 0 plus 1 is 1 sum. There's no carry, that is 0. Like 1 plus 0 is 1 and no carry. Likewise, 1 plus 1, here we get carry as 1 and the sum as 0. This is what the truth table of half adder is. And now let us move on to the K-map simplification for logic diagram. This is actually K-map simplification is done for the diagrammatic viewing of the particular K-map. And here, as we look into this, see in the carry, we had only for 1 and 1, it was output 1 carry 0 sum. For the rest all, it was 0. So in this sum, we only mentioned this 1 1 as 1. This is carry AB. And whereas here for some truth table of sum, 0 plus 0 was 0 and 1 plus 1 was 0 in the case of sum, and remaining were 1 1 1. In this way, like we will generate an expression in order to draw a logic diagram for the half adder. This is the carry equation and this is the sum equation. So as we move on to the logic diagram, see, like A XOR B we have received. So A and B, this is linked to the XOR gate, and then in the case of carry, it was only A into B. So A into B, that is AND gate. See, this is the logical expression of carry, and this is the logical expression of sum. So your logic diagram of half adder consists of XOR gate and an AND gate. XOR gate computes the sum output while the AND gate computes the carry output. This diagram visually represents how inputs are processed to produce outputs. Moving on to the next slide. Uh, Now, as we move into the full adder, it is actually developed in order to developed one of half adder. So basically in half adder we had a collision of like only we used to add only two inputs, but in this case we can add three inputs at once into the full adder. That is why it overcomes the limitation of half adder. A full adder is a combinational circuit that adds three binary digits, two significant bits, and a carry input. It produces two outputs, the same as a half adder, that is sum and carry. Full adders are essential for creating more complex addition operations in digital circuits. Now, truth table for half adder. The truth table for a half adder illustrates the outputs for all possible input combinations. It shows how the sum and carry out are determined based on three input values. See here, we give three input values and we receive the outputs as 2. 0 plus 0 0, that carry sum will be 0, and here also it is 1. In the same way, we draw the truth table for all different types of input values. The only place where we could see here is double 1 0 and triple 1. Double 1 0 gives a carry output as 1. Sum is also 1. triple one is also sum is one, carry is also one. So this is a true table of full adder. Now K-map simplification for the case of drawing of logic diagram. See, first, since we got the we'll just plot what and all we have got as ones and what and all we have got zeros into the K-map in order to derive a logical expression in order to draw a logical diagram. See, A, B, C, 0, 0. Wherever we received one as the output, that will be marked as one, and rest of the one are marked as zero. See, here we derive an expression A XOR B XOR C. Since it is a diagonal relationship, we usually mention it as XOR gate. So the sum expression is A XOR B XOR C, whereas the carry expression is like the same way we mark all ones and zeros in the K map. Like here we have these two similar and these two, and we can derive three different logical expressions. Based on this relationship, we will derive this expression in order to draw the logical diagram. So we'll move on to the logical diagram. Logical diagram of full ladder. The logical diagram of a full ladder consists of two XOR gates, two AND gates, and one OR gate. See, like here we this is some expression of the sum, and this here we are getting carry. So here AB into BC into CA we have received. So these and all are under the AND gates, AB, BC, CA, and these are all connected to OR gate because in between there was a sum operation, that is plus. Whereas coming to the sum is all A XOR B XOR C. That is why we have simply drawn an XOR gate for explaining the logical diagram of full adder. The logical diagram of full adder consists of two XOR gates, two AND gates, and one OR gate. First XOR gate computes the sum, and first two out inputs, while the second XOR gate adds the carry input. The ADD gates generate carry outputs that are combined through OR gate to produce the final carry out. Now we'll compare what is a basic difference between the half adder and full adder. Half adders can only add 2 bits, whereas a full adders can add 3 bits, which is a basic implementation of it that surpasses half adder by the full adder. Half adders are simpler and require fewer components than full adders. Full adders are used in cascaded configurations to perform multi-bit binary addition. And that's all for the presentation. Thank you for your patience listening.